Hey, Arsenal here with an extension of what we did in 2.6, dealing with patterns of functions. Well, today we want to look at particularly identifying linear functions. Our objective, we want to be able to identify and prove that a function is linear from multiple representations of linear functions. And essential question, how do I prove that a function is linear based on how it's represented? Here's some vocabulary. I'm not going to read it to you. If you have to, pause the video and jot these down. But if you noticed, there are only maybe three new terms here: the linear function, linear equation, and of course the standard form of a linear equation. We'll be using these throughout the slides, so please make sure you have them jotted down. Identify linear functions. You can identify linear functions, but first let's recap how to identify if a relation is a function. We use several means to help us identify from the relations given. We use a list of ordered pairs, we use a graph, the mapping diagram, and we also use tables. Here's an example of each. From 2.6 video, a function has exactly one output for every input. To add to this, remember every function is a relation, but every relation is not a function. You have to be a relation before you are a function. So just to review on what we looked at in 2.6 is the relation 325031 a function. Ms. Sanchez taught us to list out the input terms. So what we have here, the 3 is our input. The 5 is also an input. We don't have to write the 3 twice. We just write it once when we list it out in our domain. And for the range, we list the output values. Based off of what she taught us, we could also make a mapping diagram, which for me is easier to view. So I'm going to take what I list in my domain and list under the X column. And for the Y bubble, I'm going to go ahead and list the outputs and draw my arrows. If you notice, the 3 has 2 different outputs. In other words, it has arrows drawn to 1, from 3 to 1, and from 3 to 2. In this case, what we learned from 2.6 that this is not a function since the X repeats, or the input 3 repeats. Now the whole reason I'm going back over this is because it's real simple. We want to identify linear functions, so you have to make sure you're dealing with a function first. So simply put, for functions, the input values cannot repeat. This is important again because to identify linear functions, you must first prove that the relation is a function. So now let's look into dig deeper into our objective for this evening. Identify or prove that a function is linear. Here's our first example. Determine if the following graphs represent linear functions. To me, graphs are easier because the graph pretty much will tell you if it's linear or not. In this case, example 1, we have a line. This is a line with no curves or bends, so guess what? This graph has no curves or bends, so this is a linear function. Pretty simple. Check out the next example. What do you think? Is this a linear function or not? You guessed it. The graph has no curves or bends, so this is not a linear function. Key word here is linear. It's a straight line. Straight line, no curves or bends if you want to be a linear function. Check out the next example. Example 3. Not going to spend a lot of time there. It's kind of intuitive that I have a straight line with no curves or bends, so the graph has no curves or bends. We would conclude that this is also a linear function. Make sure you jot down notes to the left in the question box or any question that you may have to ask your teacher tomorrow. Continuing on with identifying linear functions using graphs. Take this one for a gander. Yeah, this one is a little different. This graph has no curves or bends, but the input values repeat, so it's not a linear function. Matter of fact, this is one of the exceptions to the rule. Anytime you have a vertical line will never be classified as a linear function. And the way you will prove that is you make a table and plot the points on, put the points on the table, and you'll see that your x values will repeat. I'm not going to do it in a video. I expect you to do that on your own. If you have questions, make sure you ask your teacher in the morning how to make a table to prove that the vertical line will never be a linear function. Next example. What do you think? Does this graph represent a linear function or not? I know you probably try to treat it like we did the vertical line, but in this case, this graph has no curves or bends, and it indeed is a linear function. And the way you would prove, just to make sure that it is a linear function, you would do just like we did in example number 4. Make yourself a table, and you will see that the input values do not repeat. So what happens when I don't have a graph? Well, when you don't have a graph, that means you either have ordered pairs or you have a table. In this case, we want to look at them together, because if I have a table, I can make a list of ordered pairs, or vice versa. If I'm given a list of ordered pairs, I can create my own table. So this example says, does 0, -3, 4, 0, 8, 3, 12, 6, and 16, 9 represent a linear function? We want to follow the same rules as we did before, but in this case, we want to go ahead and make our table, and I'm going to teach you another trick in order to figure out if the ordered pairs or table actually represent a linear function. So I'm going to take my ordered pairs and list them into the table. Remember, on the left hand side, we said that was the independent variable, our input, our domain, the x. And on the right hand side would give us our y term, our dependent variable. So for our independent variable, we first want to take the difference between each of these values, and thus we'll do the same for the y, the dependent side. If you notice here, from 0 to 4, we added 4, 4 to 8, we added 4, 8 to 12, 12 to 16, and we have a constant change all the way through. What I mean by constants, as you look at the positive 4, this whole side has the same number, 4, adding 4. On this side, also same constant change. From -3 to 0 is 3, 0 to 3 is 3, 3 to 6 is 3, and 6 to 9 is also 3. When you have this take place, we call it the first common difference. And when the first common difference change in x corresponds with the change in y, our conclusion will be that the table or the points satisfy a linear function, meaning yes, it is a linear function. Key thing to remember, you have to have a constant change in your independent variable, and you have to have the constant change in the y variable. I put check marks there to help you realize it has to be constant on both sides. If that's the case, you have a linear function. Let's check out another example. So here's another example just like the one we did. We have a new set of points though. Does -4, 13, -2, 1, 0, -3, 2, 1, 4, 13 represent a linear function? We want to follow the same pattern. We want to go ahead and write or fill in our table. And we want to take that common difference for both the independent variable and the dependent variable. So what do you think on this one? The first common difference for the change in the dependent variable was +2. So that satisfies our first condition. Now look at the right hand side for the change in our dependent variable. Would you say that's constant? Absolutely not. So I like to put a big X here. So what I just annotated was I have a constant change for dependent, but I don't have a constant change for, constant change for the independent, but not a constant change for the dependent variable. So my conclusion would be my pattern, I don't have it for the dependent. There's a constant change of 2 in the X, but it corresponds to a different change in the Y. Ultimately, the points do not satisfy a linear function. So that concluded that's the gist of how you use ordered pairs and tables to determine if you have a linear function or not. Now, the third and final way that we would identify if we have a linear function is by using equations. So in the worst case scenario, when you can't graph it or you don't have ordered pairs, but we give you an equation, a function is a linear function if it is described by a linear equation. Go back to the vocabulary portion to see what a linear equation is. The following are rules for using equations to identify linear functions. First rule, x and y both have to have exponents of 1. X and y are not multiplied together. X and y do not appear in the denominators, exponents, or radical signs. So here's our first example. Tell whether xy equals 4 is a linear function. Look back at your rules. Based off the rules, we could say that this equation, xy equals 4, is not linear because x and y are multiplied. It is not written in standard form, and there I have a reminder of what standard form looks like. ax plus by equals c. Let's check out another example. Example 9. Tell whether y equals 5x minus 9 is a linear function. Remember what we said, in order to be a linear function, we first need to be able to write it in standard form or as a linear equation. A linear equation is one that can be written in standard form. So for this, we're going to apply our skill we learned by solving equations, except now we want to make sure that x and the y are on both sides of the same side of the equal sign, so it can be written in standard form. If you can write it in standard form, then we can conclude that the equation represents a linear function. So this indeed is a linear function. Here's a hint I gave you. An equation is in standard form when x and y are on the same side of an equal sign and none of the three rules are broken. We have x and y both on the left side of the equal sign. They're not multiplied together. The exponents are both 1. They're not dividing one another. So we can clearly see that this is a linear function based off the three rules. Last example is coming up. Example number 10. Tell whether y equals x squared is a linear function. I think you got it. This is not linear because x has an exponent of 2 and the exponents for linear equations can only be 1. So since we have this exponent here that equals a number other than 1, this is not a linear function. So that kind of concludes identifying linear functions. And if you would, go ahead and write your summary and questions that you may have. Word to the wise, make sure you revise your notes. And something you should think about. It's a good question that you should be able to ask. What are 3 representations of linear functions that we discussed during this video? Be ready to answer those questions. See you in class tomorrow. Have a good evening.